explain it. If x defines the initial motion, if y defines the external force, and if z defines the final motion, okay? Y represents I say force, but like it's actually like how much the velocity increases or decreases from x, depending on that force. If it was a force against it, how much did it slow the speed of the object down? Get it?
Okay.
And like if it's going the same direction, so like if
can you tell me what we were discussing about again? The law of inertia?
Yeah.
So you're trying to make an equation of the law of inertia, and then you have three equations?
Yeah, totally.
Okay, so these are x1 plus y1
is equal to z1, x2 plus y2 is equal to z2, x3 plus y3 is equal to z3.
Okay, and do you have three equations because?
Okay, because of the three, like, the 3 dimensions of space. Okay. Here's how I thought of it. So, like...
Why aren't you bringing time in here? Why aren't you bringing the fourth dimension?
Because I don't believe that's the fourth dimension, that's why.
You don't believe time is the fourth dimension?
No.
Okay, alright, then carry on.
Yeah, anyways, so, like... okay, think about it like this, okay? If there's defined coordinate points, okay? If there is like, the x-axis is like a defined direction straight, right? From here. Then, what's it called? Yeah. So if the x-axis is like defined, it just goes straight. If, now think about x1 being for the, think about all of them. Think about the equation that has subscripts of 1 for the x-axis, subscripts of 2 for the y-axis, and subscripts of 3 for the z-axis, yeah. Because essentially, the way I thought about it, you can't really go either this way, or that way. Sometimes you can go this way, that way, that way. So you need three different directions. Also, considering you're going in between the directions, like if this is x and if this is y, if you're going like diagonally here, right? And you think about the initial force, the initial like speed, right? You can think about the initial speed, yeah. But what if the external force comes from a different direction completely than the initial speed? So it cuts like...
Wait. Why are you saying speed?
I'm saying speed right now because now I'm considering that magnitude doesn't matter for now. Well, not magnitude, just direction doesn't matter for now.
But wouldn't a certain force that has a direction, which is a vector quantity, will make an object go in a certain direction? So how can you ignore direction?
I guess it doesn't matter. Okay, velocity, okay? It doesn't make much of a difference. Like, if you're cutting diagonally through, then you have a completely different force, right? Just that force, if it manages to like how do you say this? It manages to either it may change the direction, or it may just change the speed of it.
Right.
So it either changes the direction or the speed.
Not both?
It could change both, yeah. So, yeah, it could do either of those. So, considering that means that if we're on the x and y plane, that means if it changes its speed only, if it only changes its speed, then it changes the speed for the x-axis and the speed for the y-axis differently. In a way. Yes, yeah. Because if it comes from this direction, then it may increase the speed by also changing the direction, right?
Yes.
But it'll increase the speed in such a way where it goes from going this way to going this way. That means if you're thinking about a two-dimensional graphically, this would increase in the x direction more, but this is increasing in the y direction more. So when you change the direction and the speed, it might increase the speed, but only for the y direction, not for the x direction.
Okay, I get your point.
So depending on from where the external force comes from, it changes the different directions, like it changes the velocity of the different directions differently.
So that's why you're saying the dependent variable, which is like velocity or speed, the direction doesn't matter at this point.
Direction doesn't really matter
because it's dependent on the independent variable
yeah, so
force.
Like x, like so.
I think I get your point. So why don't you carry on with what we were saying initially?
Yeah. So initially, you can just have x plus y is equal to z, and in that sense,
what are x and y's and z's again?
X is the initial velocity or speed. Y is the initial the external force, and z is the final velocity or speed.
Okay.
So if you just have x plus y plus z, that could be considered as any random line in a three-dimensional plane. But then you would need to split that line up into the different three dimensions. It follows. Then you'd also need to see from where the y comes from.
So is it getting more complex?
Yeah, when you add another dimension, that happens.
So what would be your end kind of equation for this?
Oh, the end equation is simply just x plus y is equal to z.
But can you solve a problem with that? Like, can you define, let's say, Newton's first law with this equation? What are you reading from there?
What?
You're reading something from there? Oh, so can you actually define?
Yeah, that's what I'm thinking about.
What?
You would start off with okay. You would simply just use the three equations together. So if the question gives you if you're given the velocity, so the speed in a certain direction, okay, in a three-dimensional plane, there's obviously a way. I haven't gotten the 3 dimensions, I've only gotten to the 2-dimensional one. But if there's a way to do it 2-dimensionally, then there's also a way to do it 3-dimensionally. Split up, if this was your line, just split it up into the
You mean the line of motion?
Yeah, if this was your line of motion, split it up into the x, the y, and the z
components.
Okay? Yeah, the x and the y and z components. So like if you were given the speed, you would the velocity, right? you will split it up and like figure out like what velocity is it going the z direction, y direction, and x direction. It's possible to do that in two dimensions, like what's the chapter called again? Dynamics and
Statics and dynamics.
no something in one dimension, 2 dimensions.
Oh, motion in 2 dimensions.
Motion in 2 dimensions. Yeah.
Like kinematics.
Yeah, kinematics in 2 dimensions.
Okay.
So just like that, if you can split up the line of motion into 3 separate.
You haven't read 3-dimension kinematics yet?
No.
Okay. So you're just extending your concept of 2-dimension to 3-dimension.
Yeah.
Okay.
So you just if you have the line of motion, okay, you have the line of motion for the external force, okay, or even if the external force doesn't have a line of motion, maybe it just slows it down. Maybe it's like internal, you know, like if it was a rocket ship, it's slowing down. Yeah. Actually, no, that would also need if we consider this to be space, then the rocket ship slowing down would also have a direction. It should have to be the opposite way. So yeah, okay. So you have your line of motion, and like wherever your external force comes from, right? Let's say let's say this is a rocket ship. Let's say your external force comes from the exact opposite direction, okay? So in that sense, if it was a rocket ship and it's going the exact opposite direction, right? Never mind. Wait, don't use that example.
Okay.
That's examples. The thing about that example is it's a much more simplified version of the thing I'm trying to explain, I guess. So it wouldn't really matter for that example. Okay, let's say you have a rocket ship and you have like an asteroid coming or something, right?
Okay.
Now this is a super strong rocket ship or something. Yeah, but so the asteroid comes, and instead of breaking it, it just shifts the direction maybe, okay?
Right.
By shifting the direction of the thing, and by also changing the speed of it, it's changed the velocity for all 3 directions, all 3 axes as well.
Yes.
Okay? So, you start off with your initial one, okay? Your initial line of motion. Find the 3 separate speeds for the 3 different axes, okay? That would be your x1, your x2, and your x3.
And those are only magnitudes.
Those are
like scalar, not vectors.
Well, they have a direction. It's just...
Yeah, usually when you resolve a single vector into different components, then they have certain directions, specifically along the parallel of the 3 axes, which, you know, it's 90 degrees to one another, right? So that's how they're resolved. It's called resolution, resolving of vectors, right? And each of those will be then called a component of the original vector. So, okay, they have directions. Now what?
Then I guess your external force. If you're given an external force, you would need to find its velocity, so speed and magnitude. Then you would then you'd separate that into its 3 separate axes.
You mean the force?
Yeah.
Okay. And each
but you'd need to find the sum. It's called not the force. Okay. Considering you have a force, you'd need to find the velocity of it.
The velocity of what?
Well, right now we're not really considering acceleration. We're only considering velocity.
Yeah, I mean, unless there's a force acting on it,
yeah,
there's no acceleration.
Yeah, so unless there's a force acting on it, there's no...
It's uniform motion. So here's what...
So, okay, wait. I'm almost done explaining. The thing is, this is a slightly simplified example. So, the way you should probably think about this example is when the rocket ship is going straight, it has one specific velocity. When it gets hit by the external force, right, which also has its own specific velocity, it goes into a second specific velocity. So there are only three different velocities in this. Okay.
The two originals and then the next one.
Yeah, like the external force.
Oh, so that's what you're saying is x plus y equals z.
Yes. Yeah.
So the z.
So you'd have to first so you convert the external force into a velocity, okay? Then you'd split it up into the three separate parts.
You can, because the mass is going to be constant. So if F equals ma,
F is equal to ma.
force equals ma, right?
Yeah.
And mass is constant all through. And you change the velocity from the original velocity of the object moving, which was your x, to...
Well, okay, here's the thing. So velocity, okay. Let's see here. So yeah, F is equal to ma, F is equal to m, and then there's velocity over time. Okay, so the change in velocity over the change in time. So it's equal to m. And there is no change in velocity over time. That would be 0. So that would make the whole thing 0. So there is no force.
Yeah. So when you don't have any force, it's uniform motion. That means there's no change in velocity. The velocity that it started with will always be that. That's Newton's first law, and that's the law of inertia of motion. So there's another inertia, that's inertia of state. It was like statics. So the moment it hit the force, or the asteroid hit the rocket, that's when it was a shift from the inertia of motion. Otherwise, it was in the inertia of motion, same velocity, right? And you have a different equation for that.
Okay, so guess I just draw it quickly. So if I have this, it's going somewhere close to okay, wait. It's going like somewhere here. And there's another force coming here. Then you just have to split this motion up into it's x, it's y, and it's z. I mean, it's it's different components. For this line, okay, this line is equal to x. This value is x. This has a value of y. And after it gets hit, okay, it goes a completely different direction, which is the value of z. So when you split it up, when you split this one up, you get x1 plus x2 plus x3, and not plus, it's just x1, x2, and x3 when you split it up, right? And same thing for the rest, and you just use this equation. But now it's much simpler because we're only thinking about it from one direction. Now if we only take like the x direction into account, right? Wait, okay. So if this is the x and this is the y, considering we only take the x values, right? Then it could be like it's going straight in the x, okay? Like yeah, it's going straight in the x, and then like a completely different force which is also in the x. God.
So how do you like the challenge?
No, it's simple to think about. It's hard to explain it to people like you.
There are people who understands less than me.
Yeah, I've met those people too.
So you think you know it already?
I mean, okay, think about it like this, okay? When you split it up into the three, okay, when you split it up into 1, 2, and 3, okay? Which is yeah, 1, 2, and 3, okay? Which is the different x, z, x, and y directions, okay? When you split it up like that, you get 3 different forces, okay? For the line of motion, when you split the external force, which is the asteroid, you get 3 more, right? So, isn't it simple? Because now you basically have 3 speeds that match up for 3 other speeds. Okay? So you just add them together. Any one of these could be negative, any one of these could be negative, they could be positive too, you know? Once you add them, certain speeds will increase and certain speeds will decrease, right?
Even certain component of the speed.
Like,
Like
yeah, I guess you could say that. Like,
yeah. Like x1 can increase when y1 is decreasing and so on.
not x1 and y1, really. It's
Why?
just like,
Isn't it the corresponding ones? The x1 component should always go with the y1 component. That's why you made that.
yeah. Here's the thing. When you
But
finally,
they will
when you
have a
finally
combination
add
of-
x1 and y1, right? You get z1.
Yeah. But the z1 is the ultimate outcome.
Yeah, the ultimate outcome. So z1 is the ultimate outcome.
Which means the changed velocity.
Yeah, so z1 is the changed velocity in the x direction.